Well, okay, hello everyone. My name is Eric Cao. I work at VMware. And my collaborator, Akhil Jain from NEC, actually spearheaded and did a lot of work for this presentation, but unfortunately isn't able to be here in person. So I'll be doing all the talking today. Now, just to get so we'll be talking about policy-driven fault management in NFV. But just to get some basic definitions out of the way, to start with, let's just say, so a network function, we'll call something a network function if it's a functional building block in a network. Examples like packet inspection, CDNs, virus scanning, and so on. Now, network function virtualization, or NFV, is the paradigm of realizing these network functions as virtual appliances. And when a network function is realized as virtual appliances, we'll call it a virtual network function, or VNF. Now, on to fault management. We all know that fault management is a must in NFV. And in fact, basic fault recovery, like responding a VNF instance that has become unresponsive, is standard in most NFV orchestration tools. But the story doesn't end there. In fact, there's a lot of complexity beyond the standard case. For example, you can think about the wide diversity of fault scenarios that we encounter, and also the wide diversity of different VNFs. So each of these combinations may call for a different fault management response. Right. Let's look a little deeper at some of the variables involved in fault scenarios. Okay, if you think of a fault scenario as a sequence of fault signals over time, well, there's a question of, are these isolated faults, or is it pretty widespread? Are we talking about existing failures or predicted failures, or even some pattern of existing failures that predict future failures? Right. There are many different fault types as well. You have hard failures, you have stability issues, you can have degraded performance, and so on. And also many different fault domains: networking, host problems, storage, application level faults, and many more. Now, in addition to the fault signals, there is also a lot of additional context needed about what is going on in the cloud to complete the picture of the fault scenario. So examples include the current and anticipated loads on the cloud and on the VNFs, includes the kind of capacities your VNFs are able to handle, and also the physical infra resource capacity that is available in the cloud. And here's a couple examples, considerations on different fault management responses. For example, if the current or anticipated load is much less than the capacity available on a given VNF, then the best thing to do sometimes is just to ignore certain fault prediction signals on that VNF. Thinking goes, if the failures do take place, some VNF instances go down, capacity reduces, and if hopefully the spare capacity is reduced, but not reduced so low that the actual load on it is affected and causing any service degradation or disruption. On the other hand, if the existing or anticipated load is very close to the max capacity of your running VNF instances, then the best thing to do may be to preemptively scale out so that when the anticipated failures occur, your VNF capacity goes down, it can prevent service disruption or degradation. Now, as a side note, that calls up another little complexity, which is if you have limited physical infra, then in some cases, when you want to preemptively scale out one VNF, you may also need to pick a less loaded or less critical VNF to scale in and make room. Now, about the characteristics of the VNFs, the idea is that different VNFs with different characteristics would require different level of handling in a fault management situation. So for example, is the VNF stateful or stateless? Is it monolithic, or is it based on a microservices architecture? There's also the interactions between a VNF and everything else that's going on. The topology, physical and virtual, that the VNF belongs in, as well as the VNF's role in service function chains. There's, of course, also the service level agreement targeted by this particular VNF. And ultimately, the most important thing is what kind of business or user impact is expected if a failure or fault were to occur affecting this VNF. So with all this complexity in terms of fault scenarios and appropriate responses, what can we do about that? All right, so one solution we'll talk about here is policy-driven fault management. And it comes with 3 big pieces. First is fine-grained monitoring and alarming. So examples of this include Monasca and Prometheus and so on. Then you also need a very rich context to be able to interpret these alarms and fault signals in broader context to know what's going on and what to do about it. And this data can come from infra managers such as Nova Kubernetes, NFV orchestrators such as Tacker and ONAP. And there is also the application level statistics as part of the context, things like low latency, throughput, and so on. In addition, any additional source of data that is needed to decide on the optimal fault management response can go into this context. And finally, to tie it all together, we need a rich policy framework. An example is Congress. And what it can do is take all this data provided, evaluate your fault management policy, and make the appropriate fault management response decisions and take those actions. A little diagram to look at the high-level architecture. We have on one side the alarm services and the contextual services providing contextual data to Congress Policy Service in the middle. Congress Policy Service then pulls up and evaluates the fault management policies defined by the operators in context of all this data to decide what the appropriate actions are, and then send those actions to the infrastructure managers and the orchestrators to effect those changes. Now, a little more about Congress. How does it work? The high-level architecture is very simple. There are 3 main pieces. First is the data. It gathers data from webhooks and APIs and stores that data as tables and as JSON. Next piece is policy. In Congress, policy is represented as a collection of data log or SQL rules. And these rules can transform data into policy decisions. Finally, there's the action piece. On the basis of these policy decisions, Congress can trigger API calls to effect changes and take fault management actions. There are many advantages to this architecture. To start with, it is very extensible because an operator can plug in arbitrary sources of data as needed by a particular fault management use case. It's also very expressive. The language is general and not limited by a fixed vocabulary or a predetermined set of properties you can set. Right, so then this way the operator can craft exactly the right policy for each fault scenario. And finally, the language is declarative by using a well-understood declarative language, you can express clear and manageable policies and avoid having procedural code in your fault management policy. Now, let's look at a simple but illustrative example of a interesting fault management policy. In this case, we look at an example of a preemptive scale out. So in a NFV deployment, when there is a predicted fault signal received, what are the possible responses? Well, one response is just to ignore it. In a cloud-native situation, that's sometimes standard, which is let the failure occur, let some instances go down, load would increase on the remaining instances, and then auto-scaling or some other kind of component kicks in to adjust. So that all works, gets everything back to a good state at the end, but there are some drawbacks. Depending on the number of instances that go down, depending on the load, there may be a period of degraded service or disrupted service. And in some applications, that may or may not be acceptable. So what's an alternative? In those cases when we don't want degraded service, what can we do? Well, one idea is to estimate the service disruption and degradation that could be experienced when predicted failures occur, and preemptively scale out the affected VNF as appropriate in order to minimize the risk of degraded service. And here we'll give a illustration of how this could be done using Congress policy. First, at a high level, using diagrams. From the data on which hosts have alarms indicating predicted faults, and the data on instances that are running on all those hosts, Congress policy can compute the instances that will be affected by the predicted faults. Then combining that with data on VNFs from a VNF orchestrator like Tacker, the policy can figure out which of these VNFs will be affected by those instances. Then again, combining with more contextual data from regarding load on these VNFs, the policy can estimate the predicted load that the VNF would experience after the faults take place. And finally, the policy can make some decisions about which VNFs we need to scale out preemptively. Okay. Now, just to be a little more concrete, I'll give a couple snippets on the policy that can accomplish some of these steps. Okay, first, let's look at the first step. In order to figure out which instances are affected, this particular data log rule can look at the table of all the hosts, the host alarm table listing all the hosts that are affected by these alarms, predicting failure. Then look up that host in the Nova servers table to figure out all the instances that are running on that host, and collect up all the results in the instances affected table. Okay, pretty simple. And just for another simple illustration, let's go to the last step as a very, very simple decision on which things to scale out. Here, by looking at the table previously computed by the policy on predicted load on each VNF, the policy identifies the VNFs where the predicted load is greater than 90% and decides to scale those out. Oh, sorry about that. Okay. All right. So that's an example. Now let's look at a demo video to illustrate how these services work together. Okay. So in this demo video, it will demonstrate the interaction between services. The first thing is that VNFs will be set up with Tacker. Then we'll configure Congress to receive Monasca webhooks. Then we will configure Monasca to send webhooks to Congress. We will then raise a Monasca alarm, and then we'll see the results of the actions triggered by Congress policy. All right, so in this video, I'm going to start it in the middle after all the VNF has been set up by Tacker. We'll have one VNF running with one instance as a Nova server. On the screen, you see the list of data source drivers that Congress can use to obtain data from different sources. You'll see Monasca webhook, you'll see Nova and Tacker and so on. That will be used in this situation. Okay, let's continue. So the first step here is to create a Congress data source driver to receive the alarm data through Monasca webhook. There it is. Here we're just listing all the data sources to see that the Monasca webhook driver is indeed in there. Okay, and it includes other sources of data, such as Nova and Tacker, and so on. Okay. Okay, so next we're moving over to Monasca to set up, to configure it to send webhooks. Oh, actually, here we're listing the Monasca metrics and finding one that we'll create an alarm on later. Okay, here it's just showing the statistics, one particular statistics in Monasca that we'll use later to create an alarm. Okay, this is where we create on Monasca a notifier to send webhooks to Congress. Okay, there it is. Next, we are going to create a Monasca alarm. Okay, and make sure this alarm calls for notification via the webhook notifier. Now you see here that the alarm is not very realistic. It's simply chosen to make sure it triggers right away. Okay, now the alarm has been created in Monasca. Okay, looking at all the Monasca alarms, we see indeed that the alarm has been triggered. And because we have the webhook set up and Congress set up to receive it, when we now go over to Congress, we should see in Congress data this alarm reflected in the data Congress policy evaluates over. Okay, there it is, the corresponding data in Congress about this alarm. Okay. So the next step is something that typically would have already been done earlier, but just for the sake of illustrating the granular steps when things happen, the flow of the data. We waited till now to create the Congress policy that will take action based on this alarm. Okay, so you can here create policy from a YAML file. And there's a policy created. Here it's just going to show you what the YAML file looks like. It has a rule that looks at all the Monasca alarms on the hosts. A second rule that looks at which Nova servers are affected by those hosts. And then a third rule that looks at which Tacker VNFs are affected. And finally, just a really simple policy action to evacuate those particular instances from the affected host. Now, in other cases, you may have different actions, such as sending preemptive scale outs through Tacker, or respond through Tacker, or many other kinds of policy actions. But here's just a simple one to illustrate the point. Okay, let's continue. Okay, and now, because Congress has received the particular Monasca alarm, now the policy is also active. It will evaluate the policy and make those policy decisions to trigger the action to evacuate that particular server. So here we should see, if we continue, that the server evacuation is being effected. Okay, yes, so yes, once we look at the list of servers, indeed, Nova has this server in rebuild status, moving it to a different host. Okay. Let's stop there. Oh. Let's head back to the presentation. Okay, so now I will just summarize what we talked about today. Number one, fault management is very complex. When you have a wide diversity of fault scenarios, it also calls for a wide diversity of possible responses. The solution we talk about here is one of policy-driven fault management. And there are three main pieces to it. First is fine-grained monitoring to create the detailed alarms that tell you the kind of faults and predictive faults we're talking about. Then there is the need for rich contextual data to be able to evaluate the overall fault scenario and what to do. Finally, there is a need for an expressive policy framework to tie it all together and make policy decisions based on all that data. Congress is such a policy framework. It features pluggable data sources, also an expressive policy language, and the ability to trigger API calls in response to these, on the basis of these policy decisions. Okay. Now, just to say a little bit beyond fault management, in general, you can really think of Congress as a general purpose framework for policy triggers. It's able to trigger arbitrary API calls to external services on the basis of policy evaluation on data. And uses of it include what we talked about today, which is fault management policies. It can also be applied to do advanced auto-scaling. And another possible thing to do is, on a slightly different angle, is to use it as a sort of generic integration glue. So if an operator wants to use events and data from one set of services to trigger actions on another set of services, right? Rather than building one-to-one integration between each of these two sets of services, and run into the sort of n-square problem, Congress can be used here to collect data via webhooks and API from the source services, evaluate the operator policy on all this data, and trigger the appropriate actions on the destination services. And there, I think in general, again, it's a general purpose policy trigger framework, and a lot of the uses are things that I probably never thought of. And if you have a case where a problem you have may be amenable to a policy trigger solution, then I would definitely love to hear from you and look at whether Congress may be helpful there. Okay. As we continue to build out Congress, we definitely would love any feedback, suggestions, and ideas. The best way to reach out to the community is through the OpenStack Discuss mailing list using the Congress prefix. And definitely also feel free to email me directly. Okay. With that, let's open for questions, if there are any.
I was curious if there is any mechanism for debugging policies. So once you've uploaded a policy in that declarative language, and then you maybe trigger an alarm, and maybe it doesn't do the action you expect, is there some way of figuring out why that didn't happen?
Yes, absolutely. So the great thing about the kind of policy language we adopted, you can either use Datalog or SQL. The great thing is that both of those languages are very standard and well understood, and they are clean, sort of really simple languages that simply build tables on top of derived tables from existing tables. So a few things you can do that helps in this case. One is you can go in and examine all the intermediate tables, right? So if the last step is, trigger this action on the basis of another intermediate table, then you can definitely look at at what point the intermediate table dropped whatever it is that should lead to the action. That's one thing. Another thing is, this is not particular to Congress, but because we use such a well-known language, there are a lot of tools available to, in the broader community to be able to debug Datalog as well as SQL, because these languages are so widely known and used. But if there are additional cases where we need Congress-specific debugging mechanism, I would love to think about what those might be.
And my other question was, since I think this is a super awesome use case for Congress and the integration with Monasca, and there's clearly limitless possibilities here for self-healing in various ways. Is this particular use case documented in a way that people could just pick it up and go with it, or is there other use cases that are already documented? You know why I'm asking this.
Right. I think I have to check on that. So this use case was spearheaded by people at NEC in their labs, and I know that there's some documentation, but I think at the moment it's not very complete. So I'll definitely have to check on that and see if we can make that more available and more complete.
Yeah, that would be great. I mean, I would love to see this documented in the self-healing documentation so that people can just pick it up, because it's, in my opinion, too good to be not better known.
All right, thank you. Okay, well, if there are no more questions, let's end it. I'll be here if there's anything else you'd like to discuss. Thank you all for coming.